In Chapter 1, we're going to be talking about how we take a frequency distribution, or just a distribution of numbers, and create a frequency table and a histogram. If you want to have SPSS open, you can if you're watching this online. Otherwise, you don't have to worry about that until you're ready to actually do the histograms and frequency tables. So let's go ahead and hop into the chapter. This chapter starts off with some pretty basic ideas. The first is that we are talking about two different kinds of statistics in this course. The first is descriptive statistics. The second is inferential statistics. Descriptive statistics you're probably familiar with. That's usually something like the mean, median, and mode, which we talk about in Chapter 2. There are lots of ways that you have measured that in the past, and you'll probably even recognize the histogram. You can see from the examples that I've given you, something like the number of people in a class, the number of females in a class as opposed to males in a class. That's a descriptive statistic. The number of freshmen, sophomore, juniors, and seniors, the time to complete a cognitive rotation task, or the distribution of race at a protest. There are lots of different ways that we can use descriptive statistics to describe a group of people. Now, inferential statistics are a little bit different. It's how we draw conclusions about a group of people and attribute that to a larger group. So we'll take a sample and compare that to a population. I know we haven't really talked about those terms yet, but that's what we're going to be talking about, is taking a small group of people, finding out how they behave, act, think, or perform, and we are going to attribute those characteristics to a larger group and make assumptions about the larger group. So, for example, do Olivet College students study more than other students? Well, we'd have to look at Olivet College students, and we'd have to compare them to some other number, usually from a population. Do the students in statistics class study more than students not taking this class? We could figure that out. We could sample people from our class and sample some other people and find out if there is a difference. And does the distribution of race at a protest match the distribution of the region from where they come? So, for example, if you see the distribution of race at a protest, and it's not at all like the distribution of race at a particular region where it's being held, you might make some assumptions, or you might have some curiosities about the type of people that are attending the protest or what the protest is about. Some more terminology that we're going to come across are things like variables. The variable is a container. It's kind of something that we use to put values in. So a variable can be something like shoe size, race, age, opinion on the use of lethal force. Those are all variables because they can have different numbers. The values of the variable are the possible responses, and sometimes we call that the range. So age has a value, or could have a potential value, between 0 and whatever the oldest person is right now. I leave it blank because that kind of changes all the time, unfortunately. It's one of those world records that you don't hold for very long. The stress level on a scale of 1 to 7 has values from 1 to 7. The length of time it takes you to complete a test, from theoretically almost 0 to infinity, or your favorite subjects in elementary school. Those are all things that could have values to them. And the individual score is the particular value on a variable. So if you ask somebody how old they are and they said 32, that would be their score among all the values. Stress level of 5 is another score. Now, something that's very important for you to focus on is the level of measurement. The levels of measurement are ways that we classify variables, and they're based on some characteristics that the variables have. The 3 levels of measurement that we're going to focus on in this class are nominal, ordinal, and scale. I say those even though they don't look like that in the slide, because we're going to use the terms that SPSS uses, because that's what we're going to be rooting most of our practice in. So the nominal variable is a variable that has no order, or the order is arbitrary. The distance between scores is not equal, or it doesn't make sense. So like species of a tree, the classification of mental disorders, or gender, those are nominal variables. They can't be rank ordered, and the distance between them isn't sensible. For example, the difference between a man and a woman, you can't put a number on that. Same thing with the classification of mental disorders. You can't really put them in any particular order, although in the DSM-5 they are in a particular order, but that's just arbitrary based on the classification system that they chose to use. Same with species of trees. The species can't be ordered in a meaningful way, even though you could argue for alphabetical. Alphabetical order is in itself arbitrary. The letters don't have to be in that order, so it really is arbitrary. Next is ordinal, which are also called rank order. So these are variables that can be ordered, but the distance between the scores is not equal. So something like political tendencies. You have liberal, moderate, and conservative. That's on some kind of spectrum of what your feelings are about the way that the political group operates. Liberal, moderate, conservative. Those tend to be on a spectrum. Now, the class standing is also a rank order, so freshmen, sophomore, juniors, and seniors. There is an order to them, so you could say that somebody who's a freshman has more credit hours than somebody who is has fewer credit hours than someone who's a sophomore. But that number could vary. You could have 12 credits and be a freshman, or 8 credits and be a freshman, or you could have 22 credits and be a freshman. And same with sophomores. You could have varying numbers of credits. So the class standing can be ordered, but the distance between the class standings isn't always equal. Also, the completion of a test in a class in terms of what order you came in. So the person who completed the test first could complete a test in 5 minutes, and the person who completed it in second place could have done it in 6 minutes. The person who completed it in third could have done it in 10 minutes or 12 minutes or a half an hour. So we can order them, but the distance between them is not always equal. The third level of measurement is scale. These are where we like to see variables for quantitative use much of the time. We use nominal variables to group things, but interval ratio, known as scale, are what we try to measure things by statistically. So the number of self-harm attempts in 1 month, or the age, or the personal bubble distance according to race, those are scale variables because they can be ordered, and the distance between the scores is equal. So the number of self-harm attempts in 1 month, if we're counseling somebody, is interesting to know. We want to know how many there are, and we want to be able to say that they are doing so much better or so much worse, and that's based on the order of the numbers. So 5 is obviously more than 4, and the distance between them is equal. So the distance between 4 and 5 is the same as the distance between 9 and 10. So when you're talking about frequency of something, typically that's a scale variable. Same thing with age, same thing with personal bubble distance according to race. So you could identify which races tend to be closer with their personal bubbles because you could measure that, and measurements tend to be scale, where the distance between them is meaningful and the distance between them is equal, and they can be ordered. So just a note is that the difference between an interval and a ratio variable is the presence of an absolute 0 in ratio, meaning that if something does not happen, it's a 0. Like time. Time is a ratio. You can't have negative time. Okay, but for an interval variable, you could, for example, temperature. And for the Fahrenheit scale, 0 means that it's 0 degrees on the scale. It doesn't mean that there's a lack of temperature. So you can kind of see that come into play with Celsius too, whereas 0 means freezing in Celsius. So the 0 is not necessarily an absence of something. It's just an indication that it is somewhere on the scale. But things like time and weight, those are ratio levels of measurement, even though we classify them both as scale, because they have absolute zeros that mean that there's an absence of something. This is a handy-dandy table that will help you to understand how levels of measurements work. You can take a picture of this, snip it off the screen, whatever you'd like to do, to be able to have that in your notes. Now, when we have a group of scores, we like to organize them somehow. So we're going to talk about frequency tables for a moment, and frequency tables allow us to visualize the breakdown of scores. It's a way to organize and describe data. So for example, let's say that I asked some people how stressed they've been in the last 2.5 weeks on a scale of 0 to 10, where 0 is not stressed and 5, or it should be, I'm sorry, that's a scale of 0 to 5, not 0 to 10. Let me fix that real quick. There we go. That makes sense. 0 is not stressed and 5 is as stressed as possible. Among these scores, we have 2, 5, 5, 4, 3, 3, 1, 3, 4, 5. So 10 people, 1, 2, 3, 4, 5, 6, 7, 10 people answered the question, and we want to be able to organize this data in a very meaningful way. The way that you would do that is by listing the values that we possibly have. So that's 0 to 5, the frequency that they occur, and the percentage of time that they occur. So let's go ahead and do that right now. So we list our values here. 0, 1, 2, 3, 4, 5. Those are the values that we have. Now we list the number of times that each one occurs. So 0 occurs 0 times. 1 occurs 1 time. 2 occurs 1 time. 3 occurs 1, 2, 3 times. 4 occurs 1, 2 times. And 5 occurs 1, 2, 3 times. And we can also put these in terms of percentages of the time that they occur. So the score of 0 occurs 0 times, so that's 0%. The score 1 occurs 1 time, that's 10%, because there are 10 scores. That means that if it occurs once, it occurs 10% of the time. A score of 2 occurs 10% of the time. A score of 3 occurs 30% of the time. A score of 4 occurs 20% of the time, and a score of 5 occurs 30% of the time. And we can just do quick addition to check ourselves. So 0 plus 10 is 20, plus 30 is 50, plus 20 is 70, plus 30 is 100. So we have it there. So our frequency table allows us to visualize how these scores occur in our distribution, how frequently. Now, a grouped frequency table allows us to cluster scores. That way we don't have many small categories. This usually happens when you have large amounts of data. So for example, let's say that we had 25 people that went to the mall and we wanted to know how many gifts each person bought. So what we're going to do is we're going to group by 5. So we're going to have a value of 0 to 4, which is 5. We have 5 to 9, 10 to 14, 15, 19, 20, 24, 25, 29, and 30 to 34. So we are going to list people into the category that they fall into. But keep in mind, this is not categorical in the same way that nominal is. What we're doing is we are creating distinct categories for each range of scores that we are interested in finding. So how many people get 0 to 4? Well, the answer is 1. 5 to 9 is also 1. 10 to 14 gifts is 3. 15 to 19 is 6. 20 to 24 is 6. 25 to 29 is 6. 30 to 34 is 2. So what that means is that one person bought 0 to 4 gifts. One person bought 5 to 9. 3 people bought 10 to 14 gifts. 6 people bought 15 to 19. 6 people bought 20 to 24. 6 people bought 25 to 29. And 2 people bought 30 to 34. And just some simple math, which we'll learn next time, but you probably already can figure this out. That means that the percentages of people are indicated thus. Now, it's nice to have the frequency distribution, or the frequency table, which is technically a frequency distribution, but the frequency table to organize our data. But we like to look at things more or less graphical when we can. So we use what's called a histogram. Now, you've probably seen a bar chart, and you might confuse a bar chart with a histogram, but there's a very distinct characteristic between them that I'll share with you in a moment. But the bars touch each other to indicate continuity between scores. So in a histogram, the bars will touch each other instead of being separated, which is mostly the big difference between a bar chart and a histogram in terms of the way that it looks. The y-axis starts with the lowest score in the range. So when I show you the y-axis, you'll see that the lowest score in the range is identified. X-axis starts with 0 frequency. So at the axis between the y and at the point between the x and the y-axis, there will be a 0 and 0 for this particular example. Both the x and y axes end with the greatest frequency or their greatest value. And for a group frequency table, the marker for each group splits the frequency bar. So let's take a look and see what that looks like. So this is our stress rating example. And what we do is a histogram allows us to take that group frequency table and display it graphically. Now, this is produced by Excel, so it's going to have a little bit of extra information like the half points, which we're not honoring because we don't have half points for our stress ratings. But as you can see, we have our stress ratings from our frequency distribution, and it looks like one person had a stress rating of 1, 2 people had a stress rating of 1, 3 people had a stress rating of 3, 2 people had a stress rating of 4, and 3 people had a stress rating of 5. If we go back to our frequency table that we developed based on this data, we can see that the value 0 gets 0. Okay? 1 is 1, 2 is 1, 3 is 3, 4 is 2, 5 is 3. That matches what we have here. And because Excel is a little bit quirky, it did not include the 0 category because there wasn't one represented. We would, because 0 was a possible choice for this particular question. So there would be a leading category down here called 0, and it would have nobody in it. We can also make a frequency histogram based on the data from our example with the gifts that people buy. So one person got 0 to 4 gifts, one person got 5 to 9 gifts. Then you can see that the frequencies are representative of what we had in our table. So we have 1 person, 3 people, 6, 6, 6, 2. That matches our frequency table, 1, 1, 3, 6, 6, 2. So if you are following along with the chapter reading, you'll recognize that the method to make this is very easy to mimic. So hopefully just presenting this to you without developing it as you're watching it was helpful. So you can see as we are developing these frequency histograms that you can kind of outline a shape here. So let's talk about the kinds of shapes that we develop as we create the frequency histogram. So the curves based on the frequency histogram can be 4 basic shapes. Really it's 3 because we're not talking about a multimodal shape, but we're only going to focus on 3. The unimodal shape is what looks like what we call a bell curve. Okay. For a unimodal distribution, this is usually something like the distribution of ages at a grocery store or something like that, where you have some kind of large number of people in the middle, maybe people between the ages of 25 and 45, then a few younger people like children, and a few older people like the elderly. Okay. That usually is what we see when we look at a frequency distribution that's unimodal. This is what we call the normal curve, by the way. A bimodal shape, and sometimes multimodal if it has more than 2 humps, but we'll focus on the bimodal shape. The bimodal shape has 2 distinct peaks here, meaning that whatever the frequency is for this particular peak, it might be represented at a different frequency as well. For example, let's say you're at a playground and it's on a Saturday and there are lots of kids playing. You might see a lot of kids here. So maybe this peak represents people who are maybe around 7, 8, 9, 10 years old in there. And then there are fewer people that are 10 to maybe 25. Then after 25, there's another peak. And let's say that's because you have the little kids and their parents. So you have, kids that are at the playground, a lot of parents are watching the kids. Not so many people in between, maybe a couple of babysitters or something. And then there might not be as many elderly. There are still some, but it really tapers off because maybe there aren't so many elderly people at the park or at the playground with their kids. Then we also have rectangular distributions. Rectangular distributions tend to be something that you're measuring that is relatively uniform. For example, let's say that this is number of people in grades K through 12 at a school system. Kindergartners, you're going to have kindergartners at about the same rate as every other grade. If this were perfectly rectangular, it would be straight up, make a corner, and go straight over and back down. But this is usually what you'll see in a rectangular shape, where you'll have some tapering toward the top. But what you can see is that for every classification, so grades 1 through whatever, you have so many people at each grade, and it's usually uniform across the top because schools tend to run at capacity because they need to fill classrooms and such. So a rectangular distribution might be something that is relatively uniform across all categories or all frequencies. Now, other than the number of modes, which is why it's called modality, unimodal, bimodal, etc., in addition to talking about the number of peaks in a distribution, we can also talk about the shape of the distribution. So a distribution that is symmetrical is the same on both sides. When we have a skewed distribution, usually what that means is that we have a heavier tail on one side than the other, indicating that even though there is a kind of a larger portion of people at a particular point, there is a large proportion that is below that certain point. And if there is, we call that negatively skewed. The housing market kind of looks negatively skewed, where the median house value might be something like $250,000, but so many more people are below that. So we end up having a larger tail toward the bottom. And then we have a positively skewed graph, which means that we have a certain point where there are many people. So like maybe the mean income in the country is centered pretty low, and then there's kind of a tail of people that make much more than that. The floor and ceiling effects are indicated by the fact that there are scores that tend to cluster toward the ceiling. For example, let's say that I made a really easy test and you all did really well on it. Well, what would end up happening is that so many people would score so well that the curve wouldn't even have a positive side. It wouldn't even start to go down. It would just run up to the top of the scores, and that would be it. So we have a lot of people that get 100% and maybe only a few people that get less than maybe a B or so. On the other hand, we have a floor effect, which is usually indicated by a cluster of scores toward the bottom. So if I asked you how many times you have been put in jail, hopefully the answer is really low. So if it's 0 all the way up to maybe 10, hopefully you have an answer that is down here in the 0, and then there are some people who will be in 1, 2, 3 times, but you're going to have many more people that say that they have 0, which is going to lead to a floor effect. As a matter of fact, you can't even get less than 0, so you're probably going to end up with the floor effect anyways. The last thing I want to talk about is what we call kurtosis, but you're probably just going to talk about it in terms of peakness. And that's more or less if you have a really pointed peak or a flattened peak. So we talk about in terms of kurtosis, which is really about the tails, but a normal distribution just kind of has a nice up and even flow and then back down. It's really hard to describe what a normal curve looks like until you've seen them, but there it is. A heavy-tailed or a leptokurtic curve is really narrow and is fairly pointy at the top. Okay, this is usually indicated by a cluster of scores that center around a single value. And then we have a lightly tailed or platykurtic distribution, which is usually indicated by some kind of more or less uniform distribution of scores, something that isn't able to have a particular distinct peak. So if we went into a grocery store and we asked people how their day is, and they rated on a scale of 0 to 7, you're probably going to get a lot of answers all over the place. And usually if you see some kind of distribution like this, it's usually because it's poor questioning, where you've asked a question on a survey or something that people don't understand, so there's no real rhyme or reason to how they're answering. You don't really have to know the idea of leptokurtic, platykurtic, etc., but it is important for you to be able to recognize when a curve doesn't look quite normal and to recognize that there may be something that's flawed about it that makes it not normal. So that's chapter 1. If you have any questions, feel free to reach out. I want you to be focusing on the histogram and describing it in terms of the number of modes, so the shape of the distribution. Is it unimodal, bimodal, or rectangular? Talking about the symmetry, the skewness, and if it has a floor or ceiling effect. And to some degree, you can talk about if it has a peak or not. So be focusing on those things, and I look forward to seeing what you can do with the data analyses.